us write the remaining equations related to velocity of the particle in simple harmonic motion, acceleration of the particle, what is its kinetic energy, what is its potential energy, what is the total energy of the particle in SHM. So, let us take equations for velocity, acceleration, kinetic energy, potential energy and total energy of what? Of a particle in simple harmonic motion. That is what we just want now. Once again, we just go by mathematical approach by considering the same earlier equations what we have taken up. I just take displacement equation first. Y is equal to A sin omega t, from which you can directly write sin omega t as y by A. Mathematically, we can understand when I imagine a right angled triangle here and considering this angle as omega t, this now becomes y and this now becomes A, then automatically the adjacent side for this one becomes A square minus y square, this being a right angle over here. So, root under A square minus y square is going to be the adjacent side of that for that angle theta, that is omega t. Now, these are the values we need to remember from that triangle. Now, come to the second equation. What is the equation for its velocity? V is equal to A omega cos omega t. I just substitute the value of cos omega t from this triangle over here. So, what is it we are getting? You just look at A omega. Cos omega t now becomes root over A square minus y square divided by A, adjacent by hypotenuse. This A gets cancelled. So, what is remaining now? V is equal to omega root A square minus y square. This is the equation for velocity of a particle or a body which is in simple harmonic motion. What are the conditions for this equation we have to remember? Just check the very first condition here. If I say y is equal to 0, first theoretically try to understand what is y is 0. Y 0 means when its displacement is 0. Where do you find the displacement of the vibrating particle 0? While crossing the mean position of rest, its displacement will be 0. Displacement 0 means not that mean the body is not oscillating. If it is not oscillating, no question of taking simple harmonic motion at all. Body should oscillate and its displacement should be 0. How come? That is possible only when the particle or the body is just crossing the mean position of rest. So, you can say if y is equal to 0, then we can say that velocity is A omega. Already we have come across earlier about A omega, which is to be called the maximum velocity of the particle in SHM. Therefore, this velocity we can call it as V max. This is the formula for maximum velocity. So, what we should understand out of this condition, while crossing the mean position of rest, the body which is in simple harmonic motion will have maximum possible velocity. Now, come to the second one please, the second condition over here. If I consider y is equal to A, what do you mean by this? First of all, you identify displacement is equal to amplitude. What is amplitude by general definition? Maximum displacement. Maximum displacement itself is amplitude. Here displacement and amplitude are equal. What is the meaning of that? displacement when it is maximum. Where do you find a displacement maximum? At extreme position of that oscillating body. That in the sense, in the case of a simple pendulum, when we consider the oscillations of a simple pendulum, at extreme position either towards your right or towards your left, definitely you find the value of y and a are equal. When displacement is equal to amplitude, then what would be the velocity? That we are getting it 0. The moment a and y are equal, y will be 0. And what is this velocity now to be called? It should be called the minimum velocity of the particle in SHM. So, when the displacement is equal to amplitude, that means at extreme position of the particle which is in SHM, naturally the velocity becomes 0 and it is to be called the minimum velocity of that particle in SHM. So, what we can understand from these two, when velocity is becoming maximum, one can even think of the kinetic energy also will be maximum at that point. And when velocity is minimum, automatically one can think of the kinetic energy which is also minimum over there. So, what one can understand out of these two, while crossing the mean position of rest, a particle which is in simple harmonic motion will have maximum velocity and maximum kinetic energy thereafter. Whereas at extreme position, its velocity will be 0, that is minimum, and even kinetic energy also will be 0, that also is going to be minimum. That is the point what we have to understand. So, these two conditions from this equation one can understand straight away. Now, take the next one please. I just write this time the acceleration of the particle. When we consider acceleration, the basic formula A is equal to minus A omega square sin omega t. That in other words, I can write the same as minus omega square y, which is acceleration. Now, let us take those two conditions once again for this equation as well. What is the first condition? If I say y is equal to 0. Already we have discussed what is the very meaning of y is equal to 0. Y is equal to 0 means while crossing the mean position of rest. I can say in this particular case, the value of acceleration becomes minimum and its value will be 0. So, what we can understand out of that? While crossing the mean position of rest, its velocity will be maximum, whereas acceleration is 0. Similarly, when I consider the second condition saying that if y is equal to a, that is displacement is equal to amplitude or displacement when it is maximum, then you can straight away understand that acceleration will be maximum and its value will be omega square y only when I consider the magnitude of it. So, acceleration will be maximum at extreme position. Velocity will be maximum while crossing the mean position of rest. So, these 2 points we have to look into. Similarly, velocity is minimum at extreme position, whereas acceleration is maximum at extreme position. So, this is the peculiar characteristic like what we are observing. As far as simple harmonic motion is concerned, when a particle is just crossing the mean position of rest, its velocity will be maximum, kinetic energy will be maximum, whereas acceleration of the particle will be 0. At extreme position, its velocity is 0, kinetic energy is 0, whereas acceleration is going to be maximum. So, these equations one need to have in memory while discussing about displacement, velocity and acceleration of any particle which is in simple harmonic motion. So, considering these equations, we now can identify what are the equations for kinetic energy, potential energy and total energy of the particle which is in simple harmonic motion. Already we have discussed about velocity of a particle in simple harmonic motion. that already we have written as V is equal to omega root A square minus Y square. Therefore, what is the corresponding equation for its kinetic energy? Basic formula for kinetic energy we all know that one as half mv square. This now can be written as half m omega square into A square minus Y square. This is the equation we have to remember as far as kinetic energy of the particle, which is in simple harmonic motion, that is concerned. Once again, the same two conditions can be taken up for this equation as well. What is the first one? If y is equal to 0, then one can say kinetic energy is maximum. And what is its formula now? Half m omega square A square. So, when we consider this one, this maximum kinetic energy, when I just write that is proportional to omega square A square, because mass of the particle will definitely be constant. Amplitude can be a variable. Omega also can be a variable depending on the frequency or the time period what we are varying there. So, if you take the same equation, you can say that kinetic energy of maximum of one particle with respect to kinetic energy maximum of the second particle. Whenever you have been asked to take the ratio, like you can write omega 1 square A1 square by omega 2 square A2 square you can write. That in other words, you can even write it like this also, n1 square A1 square by n2 square A2 square as such. Where n1 and n2, they refer to linear frequencies of both the particles or bodies which are in simple harmonic motion. Now, if you take by any chance, omega also is given constant for the same particle, then we can understand directly that kinetic energy maximum is directly proportional to square of the amplitude only. And all of you in fact have got that idea, I hope. Kinetic energy maximum value in particular is directly proportional to the intensity part. Therefore, kinetic energy maximum is proportional to A square means you can even call it intensity also is proportional to A square. That is what we used to come across in the topic of wave optics, where of course while taking up interference pattern, intensity is proportional to square of the amplitude, we people used to write it. So, I1 by I2 is A1 square by A2 square or A1 plus A2 whole square by A1 minus A2 whole square, different formulae corresponding to the same concept we used to consider there in wave optics as such. So, this is the equation for kinetic energy and what is the maximum kinetic energy and what are the conditions we need to remember for maximum value of kinetic energy. These are the areas we have to take. Now, check the second condition please. What is that second condition? If at all I say y and a are equal. Already we have discussed when displacement is maximum, that is what is called amplitude. Then we can say the kinetic energy is now becoming minimum and its value will be 0. So, at extreme position of an oscillating body or oscillating particle, kinetic energy will be 0 and velocity also correspondingly will be 0. So, this is about velocity, kinetic energy we have to remember. What about the potential energy then? The very next concept what we deal with is potential energy, which in fact is depending on the displacement of the vibrating particle. So, when once we consider potential energy half m omega square y square, we write the equation like that. This is the second equation for the second part of the energy of the particle which is in SHM, that is potential energy what we used to consider. When you take once again the first case or condition here, if y is equal to 0, then directly you can write potential energy becomes minimum and its value will be 0. What do you mean by potential energy? 0 there. One can definitely understand the total energy will be only in the form of kinetic energy for that. And once again the second condition when we take up here, if y becomes a, that is at extreme position we are dealing with, then we can say the potential energy is going to be maximum that time, and the formula is half m omega square a square. Look at that equation and this equation. This is kinetic energy maximum, that is potential energy maximum. Look at these two and compare them. So, when you come across maximum energy part of it, whether it is in the form of kinetic energy or it is in the form of potential energy, both the magnitudes will be the same. So, maximum kinetic energy, maximum potential energy, whatever they ask for, that will have the same equation for us. Even you can even write potential energy maximum is also proportional to omega square a square, or also proportional to n square a square. Like that, in the same manner you can even write the equations there as well. Now the concept, the last concept over here, as far as this order is concerned, what would be the total energy of the body in SHM? Total energy, when I consider E total, that is kinetic energy plus potential energy. Kinetic energy formula already is here, half m omega square into a square minus y square. Potential energy also we have taken it here, that is half m omega square y square. Come on, adding these two, what is it you are going to get? You can directly understand. The total energy in this particular case now becomes half m omega square a square again. So, what is your ultimate conclusion out of all these equations? What is the ultimate conclusion? Total kinetic energy, maximum total energy of the particle in SHM, maximum kinetic energy and maximum potential energy. Look to all these three equations. They are one and the same. So, what is your conclusion ultimately? Therefore, you call total energy or maximum kinetic energy, or you can call it maximum potential energy. Anything is equal to half m omega square a square. That is ultimate result you need to have in memory. So, when we consider the total energy, kinetic energy max, potential energy max, whatever you talk about, that is having the same formula, half m omega square a square. So, while dealing with a particle in SHM, everyone need to remember the equations for velocity separately, acceleration separately, then kinetic energy, then potential energy, and finally the total amount of energy the particle is going to have while in simple harmonic motion as such. So, these are the equations what are required for us to go further in the same topic of oscillations, which under simple harmonic motion we are taking up. So, the basic equations related to simple harmonic motion we have taken up. But to know much about simple harmonic motion, theoretically we are having a reference circle. That is the one by means of which you can understand that simple harmonic motion, whatever we are taking up, that includes oscillatory motion, rotatory motion and even vibratory motion, along with wave motion also. So, if you take the concept of reference circle, in fact this reference circle tells us what is the basic concept of oscillation of a body. and how that is related to simple harmonic motion. So, let us consider here there is a circle like this, and I can just take this one into 4 quadrants like this. This is the center. This point I consider that one to be A, this as B, this one as C, and this one as D. Every one of you can understand the radius of that circle is taken as R. Everywhere, of course, radius is same. Imagine for a while there is a particle which is P that is now moving on the circumference of the circle, right, from A to B, then to C, then to D, and back to A. When you take, this is the motion of the particle. How the particle that moves from one point to the other, let us consider in a detailed way how it is moving like. When I consider the particle is here, you can surely understand this gives you the radius of it. Radius of the circle, or you can call it as the distance to the point P from the center, that is O. Let us now consider here a perpendicular is drawn like this onto x axis. When I draw a perpendicular, this is now the radius we can understand. This is now the perpendicular drawn from the point P. I name this particular point as Q, which I call it as foot of the perpendicular drawn from P. So, when P starts from A, moves to B, then to C, then to D, and back to A, in one complete rotation, how this point Q that is going to move, you just concentrate on that point. Then automatically one can understand what is simple harmonic motion and what is oscillatory motion in this particular case as simple harmonic what we are considering. Suppose if the point P is here, this will be the position of Q. When the point comes to this point, this particular position, naturally the point Q will be here somewhere. When the point P reaches B, then Q will be at O. So, what we can understand out of this one, every one of you can see. When point moves from A to B, the foot of the perpendicular moves a distance equal to P and O. That means, when it completes 1/4 a rotation here, that foot of the perpendicular just completes a distance equals to the radius and reaches the center of the circle. When this point P moves from B to C, then what can you observe? The foot of the perpendicular moves from O to C now. That means, when the point P completes half a rotation, this foot of the perpendicular completes a distance equals to the diameter of the circle. When the point comes back from C to D, then you can observe once again that the foot of the perpendicular is moving from C to this point O. When once this point comes back from D to A, this foot of the perpendicular comes back to the point A again from the center, that is O. So, if you observe carefully, when the point P completes one rotation on the circumference of the circle, then the foot of the perpendicular completes one oscillation along the diameter. That means, what is the relation between these two? You try to understand that. One rotation on the circular circumference is as well equivalent to one oscillation along the diameter by the foot of the perpendicular. If it completes the second rotation, it completes the second oscillation. That means, rotatory motion and oscillatory motion are similar. What is the relation between these two? One rotation is as well is equal to one complete oscillation. Like that, the number of rotations made by the particle P on the circumference of the circle is as well equivalent to the number of completed oscillations by the foot of the perpendicular, which is taken as a Q here. That is one zone. Let me just explain you by considering a general case here. If I just cut the lower half of the circle and I reverse that one, of course, this is one way to make everybody understand what is the relation between circular motion, oscillatory motion and wave motion as such. Suppose when I cut this circle, the lower half of the circle, and reverse that one like this, just observe carefully what is it we are getting. The lower half is cut like this and is reversed this way. Are you not finding this one like a wave now? So what I can observe in this particular case is this: circular motion and oscillatory motion are similar. They have relation. Similarly, circular motion is as well equivalent to wave motion. What is the total angle in a circle? 2 pi radian. What would be the total angle in a wave? 2 pi radian. This is what we call it as crust. This is what we call it as trough. Crust plus trough is equivalent to one wave. In fact, we all know that. In crust, the total angle will be 180 degrees. In trough also, the same angle we find. So, total angle in a wave is taken to be 2 pi radian, which is equivalent to the total angle in a circle as such. So, this reference circle can make you understand that oscillatory motion, rotatory motion and even wave motion, they are all similar. They are all similar and equal, and in what sense they can be taken under the concept of simple harmonic motion. So, this is the case. But while writing different equations for simple harmonic motion from the reference circle, let us take few cases now. I just take the same reference circle over here again. This is one quadrant and this one is the second one, third and fourth, like this. This point I consider it as O. This point I take it as A. This one as B. This as C and this one as D. Let us once again consider there is a particle P that is now moving along the circumference of the circle in anti-clockwise direction in this figure. When I just join this O with this point P, this becomes the radius. When I just draw one perpendicular from this point P, and if I call this one as Q, and if I just drop one more perpendicular onto y axis, and if I just take this one as something like A, this one D, then what we can understand, you see, this OP is radius. This OQ now gives you the x coordinate of this point P, and this OD we can take that one as y coordinate of this particular point. So, one is x coordinate, one is y coordinate. Let me consider this angle to be theta. In fact, what is that angle called? That itself we officially consider that one to be phase. What is that one? Anyhow, we are going to discuss a little later in a detailed manner. So, let us consider this one, this particular radius is making an angle theta with the horizontal like this. So, mathematically one can even take this angle also as theta. Now, look at this triangle carefully, OPD. I just take that triangle. From triangle OPD, tell what is the value of sin theta. This sin theta is opposite by hypotenuse, which is y over r. And one thing you definitely can understand, whenever I consider this one like a wave, the maximum displacement of the vibrating particle from its mean position of rest, we call it as amplitude. So, as far as a wave is concerned, that amplitude, whatever we are calling it here, is similar to its radius. Therefore, this is what we call it as the maximum displacement, which of course is called amplitude, or in this particular example it is the radius. And this radius we now can call it as amplitude A. So, what is that capital A now? It is nothing other than the maximum displacement that the particle can have. What is the maximum displacement in the case of a circle? It is as well equivalent to the radius, that only we are considering that one as amplitude. When you take this equation, I now can write that y is equal to a sin theta. But every one of us we know pretty well, omega can be written as theta by t. In other words, I now can write theta as omega t. Therefore, what would be the displacement equation now? Y is equal to a sin omega t. That is the equation by means of which we develop the theory related to simple harmonic motion. So, when we consider this reference circle, it not only gives us the relation between rotatory motion, oscillatory motion and wave motion, but also it can give us the required equation for the displacement of the particle from its mean position. So, when we consider, this is actually the equation by means of which the displacement along a particular axis of that particle P, when it is moving along the circumference of the circle of radius r, that can be calculated this way. By considering this equation, let us develop different other equations now related to the concept of simple harmonic motion.